Hello everyone, my name is Daniel Mangenstab, and this is my Physics 2211 Lab 3 presentation on black holes and orbits. In this lab, I completed two different simulations. First, I estimated the mass of a black hole by analyzing the motion of a star. Then, I created a simulation of a spaceship orbiting a planet and its moon using Newton's laws of motion and universal gravitation. Objective: the goal of part 1 was to determine the mass of an unknown black hole by analyzing the motion of a star orbiting around it. The starter program generated a unique trajectory based on my account, and I used the position data from that trajectory to calculate the star's velocity at each point. From the velocity, I calculated the momentum and the change in momentum over time. Since the only force acting on the star was gravity from the black hole, I could use Newton's second law and Newton's law of gravitation together to estimate the mass of the black hole. To complete the calculations, I first determined the velocity of the star using the change in position over 1 day between each data point. After finding the velocity, I calculated the momentum by multiplying the star's mass by its velocity. I then calculated the change in momentum between consecutive points and divided by the time interval to determine the rate of change in momentum. According to Newton's second law, this value is equal to the net force acting on the star. Since the force was caused by only the black hole's gravity, I used Newton's law of universal gravitation to solve for the unknown mass of the black hole. As you can see on the right-hand part of the screen, after completing all the calculations, the estimated average mass of the black hole was approximately 1.62 times 10 to the 34th kilograms. Each point along the star's orbit produced a slightly different estimate based on the small numerical differences in the calculations, but averaging all the values provided a much more reliable final answer. The completed simulation also displayed the star moving around the black hole while showing the calculated net force and its parallel and perpendicular components throughout the motion. Part 2, Objective. In part 2 of the lab, the goal changed from analyzing data to creating a complete physics simulation. The system included a planet, a moon, and a spaceship. Unlike the first part, there was no correct answer because the initial velocity of the spaceship could be chosen freely. The objective was to simply create and calculate every gravitational force acting on both the moon and the spaceship, update their motion using Newton's second law, and find an initial velocity that allowed the spaceship to complete the simulation without crashing into either object. The trajectory of the spaceship depended entirely on the velocity that I selected. For my simulation, I chose an initial velocity of 0 meters per second in the x direction and 150 meters per second in the y direction. Using these values, the spaceship completed the entire 700-hour simulation without crashing into either the moon or the planet. During the simulation, the moon continued orbiting the planet while the spaceship followed a curved path that was influenced by the gravitational pull on both objects. Even though the spaceship did not make a perfect figure-8 orbit, it clearly demonstrated that both the moon and the planet affected its motion, which satisfied the objective of the lab. One of the required discussion questions asks about the meaning of net force and how it relates to the rate of change of momentum. According to Newton's second law, the net force acting on an object is equal to the rate of change of its momentum. The component of the force that is parallel to the object's motion changes its speed, while the perpendicular component changes only the direction of motion without touching the speed. Another discussion question asks, what would be needed to simulate the entire system? To accurately model the complete system, every object will need to exert a gravitational force on every other object. This includes interactions between the black hole, star, planet, moon, and spaceship. In conclusion, this lab demonstrated how Newton's laws can be used to analyze and predict orbital motion. In the first part, I estimated the mass of a black hole by calculating the net force acting on a star from its observed motion. In the second part, I built a computational model that simulated the gravitational interactions between a planet, a moon, and a spaceship. By selecting an appropriate initial velocity, I was able to complete the simulation without any collisions. Overall, this lab helped reinforce the relationship between force, momentum, gravity, and orbital motion while demonstrating how computational models can be used to solve complex physics problems.